Let us do some problems on conditional probability. Determine conditional probability of E given F in exercises 6 to 9. Different examples here given to us. Let us discuss them one by one. Question number 6. A coin is tossed 3 times where one pair of events given in 3 parts of the questions. Let's do the first part. Before that, let's see what is the sample space of this experiment. A coin is tossed 3 times gives us sample space consisting of these 8 outcomes. All the 3 times head, 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 tail, head, tail, head, tail, head, head, etc. These are the 8 outcomes possible when a coin is tossed 3 times. Now, we are given one pair of events, event E, head on the third toss. What does it mean? Head on the third toss. Which are the outcomes satisfying this condition, head on the third toss? Here it is head, here it is head, head, head in the third toss. So these underlined 4 outcomes are favorable to this event E. And all these outcomes are equally likely to happen because the coin is taken to be an unbiased one. So probability of E is the number of favorable outcomes, that is 4 upon total 8. 4 upon 8. Now, what is the probability of F? Head on the first 2 tosses. Which are the outcomes having head on the first 2 tosses? Here they are. These are the 2 outcomes having head on first 2 tosses. No other outcome. So, the probability of this F, head on first 2 tosses, is equal to 2 out of the total 8. Now, since we are going to find out conditional probability of E given F, we need to get probability of E intersection F. Only then we can apply the formula for conditional probability. So let us find out what is probability of E intersection F. What do we mean by probability of E intersection F? The probability of the outcomes which are common to the both events E and F. Which means head should be on the first third toss as well as heads on the first 2 tosses. We have already highlighted them. Let us see, is there any outcome satisfying both ways highlighted? Yes, this is the one. It's being underlined as well as circled. So this is the only one common to both outcomes E and F. Hence, probability of E intersection F will be 1 out of these 8. Only one common element to E and F, 1 by 8. Now, what is conditional probability of E given F? That has a formula. Conditional probability of E given F is probability of E intersection F upon probability of F. Now we have all of them. Let's put the values. That gives me 1 by 8 upon 2 by 8. Remember, conditional probability is a ratio of 2 probabilities, 2 simple probabilities. Each of them should be considered out of the total sample space. The intersection out of 8, the probability of F also out of 8. Then simplify it. It gives me the conditional probability is equal to half. Now let's go for the second part. Another pair of E and F given to us in the same experiment. E says at least 2 heads should appear. At least 2 heads. Observe which are the outcomes satisfying E. Here they are. These are the 4 outcomes in which at least 2 heads are there. These 3 have 2 heads. It has 3 head. At least 2 head. 4 of them favorable. So the probability is 4 by 8. Now its corresponding F given to us is at most 2 heads. Maximum 2 heads, not more than that. Which are the outcomes? Here they are. At most 2 heads. We do not want more than 2 heads. It can be 0 head, 1 head, 2 heads, but not more than that. These circled ones. So the probability is 7 out of total 8. Now, as we are proceeding to conditional probability, we need to get the probability of the common elements of this E and F. Which are the elements highlighted both ways? Underlined as well as circled. Underlined ones belong to the set E, circled ones belong to the set F. And these are the 3 outcomes belonging to both of them. So, the probability of A intersection F is 3 out of 8. Now, apply this formula once more. Conditional probability of E given F is probability of E given F, E intersection F upon probability of F. And apply the values that we have already calculated. 3 by 8 upon 7 by 8, the answer is 3 by 7. Next part. This time E is the even at most 2 tails. At most 2 tails. More than 2 tails we do not want. We do not want this rest all. So here we get. These are the 7 outcomes satisfying at most 2 tails. So the probability is 7 by 8. Now, F is saying at least 2, at least 1 tail should happen. At least 1 tail. That is 1 tail, 2 tail, 3 tail, okay. At least 1 tail. Here, this green highlighted portion. At least 1 tail. Yes, 3 tails are there, 2 tails are there, 2 tail, 2 tail, 1 tail, 1 tail. All of these 7 have at least 1 tail. Only this one is exempted, which has no tail in it. So again 7 by 8. Notice that these 7 are not the previous 7. First 7 were these. Next 7 are these. Now, in order to find out the conditional probability, go for the common elements. As you can already see, these 6 of them are common to both E and F. So, probability of E intersection F is 6 upon 8. Now, we are in a position to apply this formula. Probability of E given F equal to probability of E intersection F upon probability of F. Applying the values already calculated, 7 by 8, 6 by 8 upon 7 by 8 gives the answer 6 by 7. Two coins are tossed once, where even the E tail appears on one coin. F, one coin shows head. First pair. Using this E and F, let's find conditional probability of E given F. Here, since two coins are tossed once, the sample space is consisting of only 4 outcomes: head, 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 tail, tail, head, tail, tail. Now, probability of E, the first one. Tail appears on one coin. Tail appears on one coin. So, probability of E will be 2 upon 4. These are the 2 outcomes favorable to this condition. Now, probability of F. One coin shows head. One coin shows head. Which are the outcome? One coin shows head, not this. Of course, not this. Again, the same 2. So, probability of F is again 2 by 4. Now, what is the probability of the common elements? E intersection F. That is what we require to find the conditional probability. So the common elements means the elements which satisfy E as well as F. Both of these outcomes satisfy both events E and F. Hence, Probability of E intersection F also will be again 2 by 4. Now, using the formula conditional probability, probability of E given F is equal to probability of E intersection F upon probability of F. Apply these values. 2 by 4 upon 2 by 4 is equal to 1. Now the second part. This time E is no tail appears. Sample space is the same. No tail appears. So this is the only one outcome. So probability of E is 1 by 4. And the event F says no head appears. No head appears only here. So probability of F is 1 by 4. Now this time, what is a common element to E and F? E has the outcome only this one. F has the outcome only this one. And of course, there is no common element. Hence, to apply this formula, if we want to find out the intersection probability, that's going 0 here. Probability of intersection F is 0. Hence, conditional probability of E given F is, using the formula, probability of intersection upon probability of F. It is equal to 0 upon 1 by 4. That's equal to 0. A dice is thrown 3 times. Event E says 4 appears on the third toss. Event F says 6 and 5 appear respectively on the first 2 tosses. Using this E and F events, we are expected to find out conditional probability of E given F. First of all, let's see what would be the sample space of this experiment. All possible outcomes, what are they? Let's discuss it. Here, the 3 dice. A dice, when it is thrown for the first time, any of the 6 numbers can appear on it. That is 1, 2, 3, 4, 5, 6, any of the numbers. So 6 ways the result can happen. Again, when the dice is thrown second time, that dice can show any of the 6 numbers once more. 6 ways it can happen. Same with the third case. And we have to throw it 3 times. Therefore, by multiplication principle, there are 6 into 6 into 6, 216 possible outcomes. Those outcomes might be, you got 1 first time, again 1 second time, again 1 third time, we call it 1, 1, 1. Or 1 first time when you tossed, you got 1 again second time when you tossed, and third time you get 2, 1, 1, 2. Or it could have been you got 6 in the beginning, second toss resulted in 2, third one results in 5. So we say 6, 2, 5 outcome, etc. So how many are there? That is what we discussed just now. 6 into 6 into 6, 216 outcomes are there. Of course, it's not feasible to write all 216 outcomes. Few of them as sample I've mentioned here. Now, let's consider which are the outcomes among these kind of outcomes that will satisfy this condition. 4 appears on the third toss. So, we need to consider the cases like this. The third toss should result in 4. Last number should be 4, like this. So, how many outcomes could be there? So many are there. Look, last number should be 4. That is, third toss should give you 4. That means it should happen in only one way. That is exactly 4, one way. But the other 2 dice can show their values, show their numbers in 6 ways respectively. So by multiplication principle, this kind of combination can happen in 6 into 6 into 1, that is 36 ways. So number of elements of this event, this subset would be 36. 36 triplets among these sample space elements will be satisfying the condition E, that is, 4 appearing on the third toss. So probability of E will be the favorable number of outcomes favorable to it upon the total number. Therefore, probability of E is 36 upon 216, that is equal to 1 upon 6. Now, second event, 6 and 5 appear respectively on the first two tosses. What do they mean? 6 and 5 appear respectively on the first two tosses. So first should be 6, next should be 5. So what are the possible outcomes? 654, 651, 653, any. The third number can be anything. But these two can happen only in one way. That is exactly 6, exactly 5. But the third one can happen in any of the 6 ways. Any number, 2 or 3 or 4 or whatever. So total number of this kind of outcomes would be calculated as 1 into 1 into 6, that is only 6 of them. So number of elements of the event F is 1 into 1 into 1, 6 equal to 6. Therefore, probability of F is equal to 6 upon 216 is the total. Now, since we have to find out the conditional probability, we need to first of all calculate probability of the common elements intersection. Intersection means both the conditions E and F should be satisfied. Such outcomes we have to pick up. Which are the outcomes satisfying both conditions? That means 4 should be in the third toss, as well as 6 and 5 appear respectively on the first two tosses. How will the outcome look like then? It will look like this. 4 in the third toss, E says so. 6 and 5 respectively on the first and second toss, F says so. Both conditions are satisfied on this outcome. That is only one outcome. One way. No options. This is the only option. So number of elements in the common event will be, the intersection event will be only 1. So the probability would be 1 upon 216. This is only one outcome. That will be there in F also, E also. Now, let's go for the formula. Conditional probability of E given F is equal to probability of E intersection F upon probability of F. Now we have got all the values calculated. Probability of E intersection F is 1 upon 216. Probability of F is 6 upon 216. That on simplification we get 1 upon 16. Mother, father and son line up at random for a family picture. Event E, son is on one end. Event F, father is in middle. Using these two events, we need to find out probability of conditional probability of A given B. Let's look at the sample space. What are the different ways these three people can stand? Different order. 6 possible ways. Father, mother, son, father, mother, son, father, etc. 6 possible ways they can stand. How do we know they are 6 ways? The first position, any of the 3 people could occupy, that is in 3 ways. Second position, any of the remaining 2 can occupy, that is in 2 ways. Third position has to be occupied by the third person whoever is left. That is done in 1 way. So 3 into 2 into 1. That is why 6 different possible ways they can arrange themselves for the photograph. Now, this forms the sample space. These are the set of all possible outcomes. Now, which are the outcomes satisfying this condition, this event? Sun is on one end, sun on one end. Which are they? Here, these are the 4. Sun on one end, either end. Except these two, we have four options where Sun is standing on either ends. So the probability of probability of E will be 4 upon 6. Now the condition F says father is in the middle. Father is in the middle if the arrangement is this way or this way. So father is in the middle, two possibilities are there. Hence the probability of F is 2 by 6. But our intention is to calculate conditional probability, which has a formula in which we need to get the probability of the common elements. So which are the outcomes satisfying both conditions? Sun is on one end as well as father is in the middle. Common elements are these two only. Sun on one end, father in the middle. Sun on one end, father in the middle. So the intersection, the common elements probability will be 2 by 6. Now we go by the formula. This formula. Probability of E given F is equal to probability of E intersection F upon probability of F. Give the values 2 by 6 upon 2 by 6. That's equal to 1.